The doubly fed induction generator consists of a rotor which is attached to the high-speed output shaft from the gearbox. The rotor has 3 sets of coils attached to it. These connect onto some slip rings at the end. The stator surrounds the rotor. This also has 3 sets of coils inside. When the blades turn, the shaft turns and the rotor rotates, but the stator remains stationary. The rotor is connected to a 3-phase electrical supply via the slip rings. Each coil produces an alternating magnetic field at slightly different times based on the AC frequency which is applied. These are positioned around the rotor so that they combine and create an equivalent rotating electromagnetic field. The direction of the rotation depends on the timing of the phases. A controller determines the frequency and also the direction of the rotating electromagnetic field. As the electromagnetic field rotates, it induces a voltage into the coils of the stator, and this generates an AC current which we then export to the grid. If we apply a 60 Hz supply to the rotor, then we generate and export 60 Hz back to the grid. Because the wind is controlling the rotor speed, it might rotate at 1800 RPM, but it might also rotate slower than that, or it might rotate faster than that. The magnetic field is rotating, and that is attached to the shaft, which is also rotating, so these will combine. If the rotor speed drops to say 1600 RPM, that's equivalent to 53.33 Hz. So we would need a 6.67 Hz frequency on the rotor coils to make up the difference and achieve the 60 Hz. The speeds will combine, and that will produce an equivalent 60 Hz rotating magnetic field, which produces 60 Hz at the stator. If the speed of the shaft increases to maybe 2000 RPM, that's equivalent to 66.67 Hz. And that is much too fast. So we need to subtract 6.67 Hz, and we achieve that by rotating the electromagnetic field in the opposite direction to the rotor. If the rotor was exactly the required 1800 RPM, then we require 0 Hz, which is DC electricity. So we apply a constant current to the rotor, and the magnetic field rotates only with the shaft at the same speed as the shaft. And so we get 60 Hz on the rotor and 60 Hz at the stator. The controller is constantly making adjustments to the frequency of the rotor current to ensure a 60 Hz output is maintained.